Recording is on.
Yes, I can see, please.
Okay, perfect. So I guess I can start. So thank you for the introduction. So as Masoud presented, I will talk about, so in this talk I will title It's Time to Think How We Move Data from the Network to the Application. I will discuss how we can actually more efficiently move data between the NICs or SmartNICs and application in a broad sense. So first, I will start with a bit of context. So if we look at the evolution of the performance of network interface cards on one side and processor on the other side, we see that on the network side, the performance has been multiplied by 8 in the last 10 years, while the single thread performance of CPUs has mostly been stagnating. And so it means that on one side, we have exponential improvements of the device that actually brings data to the CPUs. But at the same time, the improvement of the CPUs themselves are incremental and they have been mostly stagnating. And so the issue that we have right now is that applications which need to process packets are actually struggling to reach line rate. They are struggling to keep up with the network. If we can from another point of view, we can still see that CPU performance are increasing, but they're increasing by just adding more CPU cores. So basically, to scale performance, we just add more CPU cores. And so this works only so much. And at the end of the day, multi-threading is hard. So it doesn't solve every problem. So in this talk, I will tackle this problem of CPUs being slower than networks from the data movement perspective. So one way to transfer data between CPUs, between applications, is to use RDMA. So if you want to use RDMA, it's very easy. CPU 1 can just say, OK, send this data to CPU 2. And then the NICs communicate between each other, and they move the data around. So in this case, it's very efficient from the CPU perspective because all the data movement, all the transport is done by the NICs, and the CPU don't do anything. So the drawback of RDMA is that it doesn't work on all networks, and especially if your network has packet losses, performance can quickly degrade, and you can have issues. On the other hand, so if you don't want to use RDMA, you are basically stuck with what we call the packetized interface. So basically, you can just transfer single packets in the network between different hosts. And so basically, that's why we should build new NIC CPU interface, because on one hand, we have RDMA, which is really fast, but really rigid and has many drawbacks. And the other hand, we have just the packetized interface, so just transfer normal packets, TCP, UDP, whatever, which is very flexible, but which is very CPU intensive. So as an example, I will take the example of network function. So a network function is just any application that receives a packet from the network, modify the packet, and send it back. So you can imagine, for instance, that you have a load balancer, that you have a NAT, that you have a firewall, that you have whatever you want. So for this kind of application, it's been understood for a long time that if you actually want to extract performance, you shouldn't just process packets one by one. What you should be doing is that you should have your application, separate the application into sequential tasks, and then you should receive a batch of packets, and then have this batch of packets go through the different tasks one by one. So basically, what you want for network functions is batching to increase performance. But if we look at the NIC perspective, so how the NIC transfer packet to the CPU, basically it's fundamentally a per packet interface. So there's a disconnect between how applications want to receive packets and how the NIC actually transfer those packets. And so maybe you can say, OK, I don't care about packet processing, I don't care about NAT, firewall, or whatever. But at the end of the day, you probably care about some networking application. Maybe you care about web, about cloud. Maybe you want to do AI training or AI inference. And as Masoud said, in this case, networking is important because at the end of the day, you still need to bring data from the network to the CPU. And in this case, if you just use the packetized interface, then the interface itself can be a bottleneck for your application. So I talk a lot about the packetized interface, but now I'll explain a bit how it actually works in practice. So here we have a CPU and a NIC, which are connected by PCI Express. And so imagine that you want to receive a packet. How does it actually work? So on the CPU side, you need to allocate a buffer. Then you need to the CPU need to tell the NIC, okay, here is a buffer you can use to receive a packet. And once a packet arrives, the NIC can directly write the packet to this buffer, which is in CPU memory. And here already we have our first problem with this packetized interface. So imagine that we first receive the blue packet, which goes to one buffer, and then we receive the orange packet, which goes to another buffer. We have no guarantee in practice that the two buffers will be close to each other in memory. And so it means that in practice, time locality of packets does not imply space locality. And so already we see that this interface is not efficient from a cache perspective, because if I need to process a batch of packets, I will need to jump all around memory to try to receive and process those packets. So this is not efficient. Finally, once a packet has been received, the NIC needs to notify the CPU that, okay, actually the packet is received and you can start processing it. And it does it through what we call a descriptor. So it's just some metadata about the packet. So for instance, it contains a pointer to the buffer that was used to receive the packet. And actually nowadays, the CPUs are not the only devices that can directly communicate with NIC and that can receive packets. Actually nowadays, because of AI, a lot of GPUs can also directly communicate with the NIC. And actually, they're pretty good at it. So Maxime, a PhD student in our team, recently published a paper at PAM 26, where among other things, he benchmarked a lot of different ways GPUs can be used to process packets. And on the left, we have one of his findings. So on the graph, we have the throughput on the y-axis and the packet size on the x-axis. And the application is just an application that computes the checksum of every received packet. So you receive packets, you compute the checksum, and then you forward back the packet. And what we can see is that if we, depending on the workload and the packet size, the GPU can actually outperform significantly the CPU. And so one of the conclusions of the paper is that actually if your application is really computationally heavy, then a GPU may outperform a CPU. And to understand why it is the case, so as I said before, in packet processing, we like receiving batches of packets. If you look at the case of the CPU, if you receive a batch of packets, the CPU still needs to go through each packet one by one to process them. But on the GPU, the approach is different because the GPU has many threads. And so when you receive a batch of packets, you can just process all the packets in the batch in parallel. And so this is much more efficient. And if you look at back in the days, there was a lot of literature about packet processing on GPUs. But one of the issues was that before we need to wait a long time before we receive a batch of packets big enough so that the GPU processing is efficient. But nowadays, since the networks are becoming faster and faster, actually you reach those batch sizes much more quickly. So when before there was a latency penalty for using a GPU, nowadays there is none. And so GPU are, I think in the future will be really interesting in packet processing. So another reason why you would use a GPU. So imagine that, for instance, you want to do some traffic analysis, right? And you want, for instance, to infer some metric about your traffic. You want to infer video streaming quality, or maybe you want to infer which application is running on top of an encrypted TLS session. So in this case, you want to do inference. And actually, if you use a GPU for I/O as well, you can collocate both I/O and the application itself. So you can have the I/O, you can extract the feature, and then you can run your model all on the same device. So you don't need to move data around to do your processing. So this is much more efficient. So now I will continue with some other limitation of the packetized interface I started to describe before. So one other issue with this interface is the communication pattern between the NIC and the CPU or the NIC and the GPU. So imagine that a new packet arrives. So to receive this packet, the NIC needs to first read the buffer. When it has read the buffer, it can write the packets, and then it can write the descriptor. And so it means that for every packet that needs to be received, you have this round trip. So in practice, there is some optimization, but fundamentally the ideas remain. This interface is a per packet interface, which is not suitable for most applications. So as I said before, when you receive a packet from the NIC, you also receive some metadata about these packets. So this metadata can be the hash of the packet, can be a pointer. We can also have more detailed information about the received packet. You can know if the packet has been tunneled or not. But the problem is that this metadata is actually vendor specific and even model specific. So it means that if you change your NIC, then the metadata offered by this NIC is completely different. So this is actually one of the roles of the driver, to take this metadata, which is really specific to the NIC, and make it to something more generic. So the metadata go already once through a transformation. And then also, if you have a packet processing application, they also generally need to rely on also some per metadata, some per packet metadata space for their own need. And so you have another transformation. And so it means that before you even start in processing your packets, even before you start doing something with the data, you already go through two descriptor transformation. And so this is very inefficient. So we believe that currently the packet descriptor we are using are inadequate. They are very large structure. Most of the fields are generic, and most of the application don't even use all the fields. So you just basically increase compute and memory pressure for no reason. And so we believe that actually the NIC itself should construct the final descriptor, the final metadata which will be needed by the application. And so to realize this goal, we need to first answer one question: how can the NIC and the GPU actually communicate what they each want and what they can each offer? And to solve this issue, Ahmed, a researcher in our team, published OpenDesk at Hotness 25. And the idea is the following. So on one side, we have the NIC that can provide some metadata. And on the other hand, we have CPUs, which want some metadata. And they will each write a program to describe what one can provide and what the other can do. And then OpenDesk will synthesize those programs, and on one side generate code on the NIC to extract the metadata we actually need. And on the CPU side, it will generate code to retrieve the constructed metadata. And if some metadata is missing, then it will construct helpers to compute those metadatas. And it does that transparently for the application. So if you have a NIC that supports less feature, you will just compute the metadata in software. But if your NIC has more feature, then you will directly retrieve those computations from the NIC itself. So you may think that actually, do we actually need all those descriptors, all those transformations? Why are we actually bothering with that? And to explain why we actually need the metadata with the packets, I will take a small example. So let's imagine that you want to run a small application that wants to detect if a packet has been tunneled. So you may think why I would need to do that. So for instance, imagine that you're running a NAT and you actually don't want to NAT the tunnel packet for some reason. So there is two ways to detect if a packet has been NAT or not, has been tunneled or not. So the first way to see if the packet has been tunneled, so if it has been encapsulated, you can just manually parse the packets and see if you see some tunneling protocol. On the other hand, you can also say, okay, maybe my NIC can do the parsing for me. And so it can do the parsing and pass this information directly in the descriptor. And so the question becomes actually, how much do we gain by not parsing in software, but instead relying on the hardware? And so we actually tried this experiment. So we have two applications, one which both try to find if a packet has been tunneled, so encapsulated or not. On the red side, we have a packet lookup. So this is the software variants. And on the blue side, we have the hardware version. So in this version, you just look up the descriptor to see if the packet has been tunneled or not. On the x-axis on the graph, you have the CPU frequencies. And on the y-axis, you have the time it takes to process a single packet. And so here, lower is better. And we can see that if we don't parse the packet manually, but instead rely on hardware to give you this information, we have a 30% reduction in the time it takes to process a single packet, which is a large improvement. So yes, indeed, descriptors are important. And so now that we saw all the limitation of the packetized interface, we can think about, okay, what actually should the correct interface look like? What it should actually be? And this question has been debated in the community. So one previous work, Enzo proposed to actually replace the packetized interface by a version where all the packets are just directly written to memory. So instead of having descriptor that have pointers, so instead of having indirection, you just receive packets one after the other, and your NIC will just write them one after the other in main memory. And so it's much more efficient because instead of having buffer all across memory that contain packets, here all your packets will be just next to each other in the same buffer in a way. So what happens when a new packet arrives? It's simple. You just look at, the NIC just look at where the last packet stopped, and it just writes the next packet just after this one. And then the CPU can just directly receive these packets. And so for a very large class of application, this is a very good solution. But let's say that now you actually want to do some application which don't process the packets in the order they're actually received. So imagine that you have a switch, or let's say that you want to do traffic analysis where you need to reconstruct some streams, or you just simply run a TCP stack because your application runs on top of TCP. Then in this case, you would need to copy the packets to avoid the head of line blocking, because so if you don't copy the packets, the NIC cannot advance in the ring, and so we cannot receive the next packet. And the other problem that Enzo has is that if you remove the metadata, then you don't have any communication channel between the NIC and the CPU. And we just saw before with the example of the tunneling that metadata is important. And so to solve this problem, we proposed ASNI, which stands for Application-Specific Network Interface. And the idea with ASNI is to say, okay, maybe we don't need to reinvent the whole interface, but instead we can build on top of it. And the idea is the following. So if you have the packetized interface, what you have is that you have the idea of one buffer equals one packet. With ASNI, we say, okay, we still use individual buffers like the packetized interface, but instead of having one packet equal one buffer, we have one buffer that will contain a batch of descriptor and a batch of packets. And in this big buffer, there will be two components. On one side, we'll have the descriptor, and on the other side, we'll have the packets themselves. So we have batching both at the descriptor level and at the packet level itself. And this big frame that contains the descriptor and the payload, we'll call it an ASNI frame. And so when you think also in terms of memory management, it's much easier because instead of managing one buffer per packet, we need to manage one buffer for a batch of packets and descriptor. So it's much more efficient. Furthermore, when you look back at the problem of the head of line blocking of Enzo, we don't have that in ASNI, because if we didn't finish to process one ASNI frame, we can just allocate a new buffer and receive a new ASNI frame in the new allocated buffer. Since the ASNI frame are not collocated in memory between each other, but only the packets and the descriptor inside each ASNI frame are collocated in memory. So we remove the head of line blocking. And so if we compare ASNI to the other interfaces, so first we see that compared to the packetized interface, we have better cache locality for descriptor, we have better cache locality for packets, and we have a more efficient NIC-CPU communication patterns. We also remove the need to have all those descriptor transformation because the descriptor is actually tailored to what the application actually needs, and we have a more efficient buffer management. So compared to Enzo, we also have still 0 copy for every application. So even if we don't process packets in order, we don't need to copy them. And also we keep the descriptor, the metadata channel between the NIC and the CPU. So to test already, we built a prototype. And so to build this prototype, we used a SmartNIC. So a SmartNIC is, you can just think it as a NIC, so a network interface card, plus some programmability, which can be an FPGA, which can be just CPU cores, and this gives you a SmartNIC. So SmartNIC I use in practice to pre-process traffic before it reaches the CPU. And often the goal is to push work from the CPU to the SmartNIC. And to prototype ASNI, we use a BlueField-3 SmartNIC, which is a very commonly used SmartNIC in the literature, which has 16 cores and 32 GB of memory. So I will start by giving a high-level design of ASNI. So imagine that you have packets coming on the NIC. They are received on the SmartNIC. There we use the ARM cores to construct the descriptors which are tailored to what the application needs. And then we rely on the hardware to serialize all the payloads and the descriptor inside a single ASNI frame and transfer them to the host. So this part is very efficient because the copying of all the metadata and the data itself is not done on the ARM cores themselves. It's not a software solution. It's really done on the hardware of the ASIC. And so in terms of performance, we can go really high. We don't have any performance bottleneck here. And so once the ASNI frame has been transmitted, the CPU can just retrieve the frame and start processing it. So now we have the question of how we can actually organize the ASNI frame. So we know that we have an ASNI frame, that we want to put descriptors and packets together in this frame, but how we should actually organize this frame. So to answer this question, we tried multiple versions. So we tried first the DD version, where we have all the descriptor at the beginning, then all the packets. We had the DP version, where we interleave descriptors and payload. And then we have the PP version, where we have all the payloads and no descriptor. Second question we want to answer is actually how much do we actually batch packets inside the ASNI frame? And to answer this question, we tried a packet counter application. So this is just a very simple micro benchmark where we just receive packets and then we count the number of packets on the CPU. Here, our baseline is DPDK. So DPDK is just a set of very high performance user space drivers which are used for packet processing. And this is basically as fast as you can go using the packetized interface. So here we have two graphs. So on the left, we have the throughputs. So higher is better. On the right, we have cycles per packet. So here, lower is better. And on the x-axis, we have the batching size. So the first thing we can notice is that actually, even with very small batches of 4 packets, you already have much more performance. And starting from batches of size 16, you have a 2.3x improvements in terms of performance. Furthermore, if you look inside all the DD applications, inside all the ASNI applications, we see that the DD version, so the version that puts the descriptor at the beginning, is by far the most efficient. So we see on the left that it has higher throughputs, and on the right, it consumes less CPU cycles to process the packets. And so we can think about actually why is this DD version better? Why is putting the descriptor together better than spreading it across the ASNI frame? And when you think in terms of memory accesses, actually it makes sense. Because if you put them all at the beginning of the ASNI frame, then a single memory access, a single cache line access, retrieves all the descriptors. You have all the metadata about all the packets with a single memory access. On the other hand, if you instead want to use, if you instead scatter those descriptors across memory, which is done with the DP version, which is also done with the packetized interface, then in terms of memory accesses, you need to go through the whole frame. So you need a lot of memory access to retrieve all the descriptor. So this is much less efficient. So DD is better. Why? Because we have less cache line accesses. So in addition to those micro benchmark, we also run a lot of real-world applications. So we run 3 of them: a load balancer, a NATS, and a key value store. And in this talk, I will only focus on the load balancer. So this is our setup. So we have a hardware generator which measures latency, throughput, load rates, and we connect it directly to our device under test through a high-speed link. Here, the hardware generator is important because since ASNI has very high performance, if we want to test it, we also need something which has very high performance. And in this case, we had to use a hardware generator to match the performance of ASNI. And so here's the result for our load balancer. So on the y-axis, you have the latency, so lower is better. And on the x-axis, we have some rates. So the way we generate this graph is to set increasing rates on the generator. We measure the latency, and then if we have more than 1% loss rates, we remove the points. So that's why there is more red points than blue points, because ASNI managed a higher throughput without packet losses. So first, if you just look in terms of latency, indeed, ASNI has a smaller overhead because we still need to go through the SmartNIC before transferring the data to the host. But in terms of throughput, we see that we have a 2.3 increase. So for a small latency cost, we have a very high throughput improvement. And so that's why we argue that ASNI or ASNI-like interfaces should be a core feature of NIC. We believe that it should benefit many networking applications. So here we mostly talk about just packet processing applications. But if you have end host applications, instead of receiving individual packets, receiving chunks of data all at once is much more efficient. So we believe that those kind of interface will be available on all high-end NICs. And I think future interesting work would be to implement those kind of interfaces in hardware, on ASIC or on FPGA. And we believe it is possible because the building blocks are mostly there. So if you look at what is currently possible on some NICs, they already support some NICs already support multiple descriptor formats, and LRO and TSO, so the ability to gather packets and split packets, is already present on modern NICs. So the building blocks are almost there. We just need to put them all together. So I will finish by some related work to end-host applications. So one interesting related work is device memory TCP. So imagine that you have an application that want to do inference or training or whatever. So basically, you want to push data to the GPUs directly. In the case, you can use this technique, which is now upstream in the Linux kernel. So in supported hardware, the packets arrive to the NIC, and then the NIC splits the packets into two parts. So first the header, so the TCP header, and the rest, the content of the packet, so the payload. The header can go to the CPU so that you can run a normal networking stack, and the payload goes directly to the GPU. So you don't need to copy the data between the CPU and the GPU. The NIC can directly push data to the GPU. And with this approach, it's very nice because we remove the copy between CPU and GPU for the payload, but still all the packets are still scattered across memory. So if you want to reconstruct your stream of data on the GPU, you still need to copy the data on the GPU itself. And those kind of features are also available on other frameworks like DPDK. So it's not only on the Linux kernel. To go further, ZeroNIC proposed to keep this idea, but to improve on top of it. So here, instead of having, so here we could keep the idea of having the header that goes to the CPU to be run on to execute the networking stack. But here the payload can directly go to the GPU, but it doesn't just randomly go to a random buffer. Here the buffers are, so here the payloads are collected per stream. So if you have a stream of data, and you have the next block of the stream that arrive on the NIC will write it just before the previous one. So basically it means that the NIC can directly reconstruct a stream of data. So you don't need any copy on the GPU, you can just receive a stream and then start processing the data directly. So obviously this is much more efficient because you don't need to copy stuff around inside the GPU. But you need some specialized hardware. So in that case, they really need a very specific NIC to make this system work. So for future work, I think that building NIC CPU interfaces for other type of application is a really interesting future work. So for instance, so imagine if your application rely on TCP again. So currently you're probably running TCP on your CPU, but you can also imagine that the NIC itself should be running the networking stack. So not just only RDMA, but other more flexible stack. And so more broadly, we believe that the NIC and the CPU shouldn't exchange just packets, but should exchange structured data. And this structured data should fit what the application actually needs. And so if you want to collaborate on this topic, I'm more than open to do that. So to conclude, we saw that NIC CPU/GPU interfaces are a very active field of research, both in the packet processing world and also in the end-host application world. We also saw that GPUs are suitable for high-speed packet processing, especially when the workload is really high and the number of packets that need to be processed is relatively low. We also saw that NICs are very heterogeneous, so that's why drivers need to be very generic. So this causes a lot of inefficiency. So we believe that actually the drivers should specialize to the application and not the other way around. So the NIC should specialize to the application, and it's not the NIC that should adapt to the, it's not an application that should adapt to the NIC. And finally, we saw that we built ASNI, which is a new interface that outperforms the classical packetized interface by 2-3x in terms of throughputs at a very small cost in terms of latency. So this concludes my talk. So if you have any question, feel free to ask them.
Thank you very much, Nikita. It was a very interesting talk. And actually, it's also my research interest. So if there is any questions, please please raise it here. Any questions? Otherwise, I have. Okay, so maybe okay. Okay, we have some compliment, not question. But I have actually a question. It was very interesting. Actually, one of the challenge that I had when I wanted to use the RDMA, I noticed that if I wanted to, for example, use the SmartNIC type of NIC general, I see it. Okay, if I wanted to use it as like a processing on the path, the packet needs to basically the data packet needs to sit in the SmartNIC and then continue the way to go to the memory up. Or I can bypass it and directly go and then sit on the memory. And that one I need to register the memory, for example, before to the RDMA, and then I make it available to the like other nodes in the cluster, and then I can communicate. But regarding ASNI, if I want to think about how's your setup, so basically ASNI is running on the ARM cores on the Bluefield tree, and so it's basically processing there. So when the packet comes, it should sit on the memory on the Bluefield tree and then process there, and then but this is basically the packet is pushed up to the host. Am I right?
Yeah, exactly. So that's why we have the small latency penalty, because you still need to receive basically the packets to our memory or DRAM if it exceeds LLC, and then once. So you do that, and then you process the packets, you create the ASNI frame, and then you send it to the host.
To the host.
And so another issue with this approach is that the NIC need to copy every packet twice, basically, because the packet comes once to the ARM, and then the NIC needs to copy it again to the host. And so we saw that especially at very high rates, the NIC is really struggling to do that because it's twice the work, basically. And you can imagine that if the packets, the ASNI frame comes also from the other direction, you also still need to copy it twice because the frame comes back. Then the ARM cores need to segment the packets, and then you need to send them on the network.
Yes.
So in the prototype, actually, it's quite computationally heavy. So that's why we argue that actually this should be a feature which is built on ASIC, this ability to create those big frames and transfer them.
Yes, exactly. So it's just like a proof of concept that actually can be implemented by FPGA or maybe even directly, like we have with ASIC.
Yes.
But in the current version, how do you communicate like pushing the packet from the Bluefield to up? Is it like a DMA Doka or like RDMA there?
Yeah. So actually, we tried multiple ideas. We tried DMA, because there is a proprietary DMA API from Nokia, where you can, from the CPU of the ARM cores, copy data to the CPU of the host. But the problem we had is that if you want to do this gathering step of having payloads all around memory and create a frame and then send the frame, the API was not very efficient at all for that. There was some internal limitation, and since the code is closed source, you cannot really modify it. And so at the end of the day, we just send a big Ethernet frame, because then we can reuse all the DPDK and all the existing infrastructure. So basically, we just create a big packet and we send the big packet to the host. But as you said, you can use RDMA is the same.
You can use it. But then, okay. But how do you control the memory management that you mentioned to be like in the order?
Sorry.
How did you manage the memory management to be like, as you mentioned, that we have one packet, the other one sit exactly on the next one.
So for this actually, it's a feature of most NICs. It's called the scatter gatherer. So basically, you can just pass a list of segments to the NIC, and then the NIC can send it as a single packet. So basically, it does
Okay,
the
okay, yeah.
serialization for you in hardware, and actually, it's really really fast. So we test it on the Bluefield, and you can have up to 52 segments of memory that can be sent as a single packet.
Yeah, okay.
So the NIC itself can look up 52 different segments. So it can go for a linked list of 52 segments and then just send them as a single packet.
Yes, this is great. Yeah, nice. And so then yeah, so as I see that this is going to be a feature for the like NIC as a core feature of the NIC. Yeah,
Yes.
very interesting. Yeah, very interesting. And could it be uh, like flexibility to modify it, but it is like it is fixed, and then it should be like or there is like, do you think that it can be like there are some parameters that can be tuned, or just like or it should be just a fixed
So
functionality?
here currently we have some parameters which can be tuned. So for instance, we have some kind of timeout to wait for packets to be received for the frame. Because imagine that if your throughput is very like high then low, so it's very like not continuous, that you can imagine that in some case, if you wait for 32 packets, for instance, you will wait a long time, and so you will add latency to your system.
Yeah.
And so I think one of the things you can actually like choose is the time the NIC waits for new packets, or number of cycles it waits to before you flush the frame anyway. Because maybe you want like 16 packets inside each frame, but maybe you need to wait too much, and so you have only 6 packets, and then you can just flush the 6 packets. And even in this case, I think it still works because, as we saw before, even very small batching already increases performance. Like if you just batch 4 packets instead of 1 packet at a time, you already do better than what DPDK can do.
Yes. Okay. Nice.
And so I think one of the idea of the paper is to to not complicate the design too much, because we believe that yes, it should be on actual hardware. So if you make a design too complicated with too much parameters, then it won't be implemented actually, like for real.
Yes. Yes. And is it like I don't know, is it publicly available to?
Yes. So there's a repo and you can look it. The code is all there.
Okay, great. I don't know if there is any question we can ask Nikita. I don't know if there is any other question, or I need to continue. It seems there is no questions. So I
No
have one
question.
more question, Nikita. So what was the challenges? I mean, the most challenging part for the when you deal with this idea?
I think honestly, one of the hardest part was just figuring out how you can actually implement the design, because there's many ways to communicate between the NIC and the host. There is
Yes,
many
exactly.
technology
Yeah.
NVIDIA offers, and I think we just spend a lot of time just trying every single ideas, and just at the end of the day, finally picking the one that works. So for instance, another idea we tried, which I did not discuss, is that so currently the descriptors are just constructed on the ARM cores. And at some point, we try to actually make them in hardware. So when you look at the Bluefield tree or the Connect 6 NICs, they actually have a very powerful ASIC pipeline. So the idea was the following. So you receive a packet, then you encapsulate it with some random like VXLAN or whatever. And then this VXLAN header will act as the metadata. So the NIC will look in the packet and will construct the metadata in place of this VXLAN header. And then packet arrive on the ARM, you just split them, and then you reconstruct the lists, and then you send them to the host. And so in theory, it's very nice, because then you rely on the ASIC to construct the descriptor itself, so the ARM doesn't do very much work. But in practice, it doesn't work because the pipeline is not fast enough to encapsulate, construct the descriptor, and then send them to the ARM. So yeah, so I would say the biggest challenge is just the limitation of the hardware itself and all the variety of possibilities you can actually explore to realize the design.
Yes, exactly. I think that there are some features, and probably some features still maybe it's not completely like mature enough to see that how is it,
Yes.
or some of them. Yeah. So then, but then now I see that. So at the end, you convinced that you don't use DMA Docker. So then you try to use the because of the.
Honestly, I would use RDMA. Like Maxime also used RDMA to communicate between the NIC and the host. And here we didn't have any performance limitation. So
Mhm.
RDMA works for sure. DMA, I saw some recent paper that use it for some stuff, but still it's proprietary. So if you have an issue, you cannot fix anything.
Yes, we can fix it. Yes, still you have
Uh,
more flexibility with the RDMA, but also the problem of the RDMA is that like maybe there are not so many like different operations support really like read write, and it's not. But of course, it's enough. But if you have
yeah,
more, then that would be cool.
yeah, yeah. So,
Yes.
so if you want to communicate between two, there's also if you have the Bluefield tree, there are some DPA cores on them. So those are like some RISC-V cores, and they can use MMEO to write to host memory. And why it's interesting because MMEO is much lower latency than DMA or DMA. So if you just want to pass control messages, there is also other paths that you can use to transfer those messages, not only DMA or DMA. You can also do MMIO if really latency is important for you.
But do I need, is it like a future or like a library, a new library from Docker to communicate?
Yeah, so you need a Bluefield tree first,
Yes.
and then yes, and then yeah, you need a Docker library to communicate. But it's very low level, so you can
But
do a
is
lot
it,
of stuff yourself.
what is the name of the library or the name of this
So it's called Flex.io, and it's the
Flex.io?
DPS.
Okay, very nice.
Yeah, and it's the DPS stuff. And it's, for instance, if you want to customize RDMA, they have also a whole library that you can use those very small RISC cores to customize RDMA.
Okay,
You can
great.
intercept RDMA messages and events, and then you can insert your own. It's very flexible.
Oh, that is nice. As a, but I need to, as you mentioned, I need to have the Bluefield tree.
Yes,
Yes, great.
I,
Yeah,
I think
Bluefield
Connect 8 works.
Connect X8.
8, yes. But 7 doesn't. We tried. Actually the core are there on the Connect 7, but you cannot use them unless you have like an NVIDIA key to sign the binary.
Yeah, that is the.
So, it
Yeah,
doesn't
so there
work.
is a big, basically, like improvement from Bluefield 2 to Bluefield 3, since
It's
there are
huge. Yeah,
more.
it's huge.
Yeah, it's a
It's
more
huge.
more supporting features. And it seems that at the beginning Bluefield 3 was a little bit disappointing, but Bluefield 3 there was more like more features, and that's interesting.
Yeah, yeah, for sure.
Uh, yes, thank you very much again. It was
Thank you.
very interesting talk.
Thank you
If
for the
there is
invitation.
any other question, otherwise I can share. Basically, I stop sharing for